The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our next presenter is a professor of engineering and director of the Pankow Materials Laboratory at Purdue University, Dr. Jason Weiss. He's going to give a presentation on cement, fly ash, and limestone blends, providing constructability to sustainability.
Thank you very much. What I'm going to try to do today is give a little bit of a buffet of some of the things that we're doing, 5 or 6 slides and some different technologies, and if that whets your appetite and you want to discuss it more, I'd be happy to chat with you after the session about it. But a lot of the things we're going to talk about are things that are being on their way to being implemented in field concretes. And this goes great collaborations on this and a lot of work from a variety of different students. First part will be talked about by some of Tim Barrett's work. We also have some work from Hung Fang Sun, Igor de la Varga, and then several parts of this we've done in collaboration with Dale Bentz from NIST. So without further ado, I want to jump into this and start to get into some of the discussion on where we're headed with these different blended systems. As most of us know, the real push toward a lot of these solutions is really the sustainability driver. And the sustainability portion of this is what we're going to start out with. So we're going to give a little bit of motivation. Then I want to get into some commercial Portland limestone cement systems, talk a little bit about some alternative approaches for grinding, talk about some set acceleration, and then internal curing with high volume fly ashes. So you'll hear a lot about CO2 production, you'll hear a lot about green technology, and the real reason we're looking at this is somewhere between 5, from the pie chart here, we'll say 5 to 8% of the world's CO2 comes from cement production. And if you hear this, and on a college campus we hear this a lot from students, they're shocked, 5% or 8%, we just have to stop using cement. That may be easier said than done, and the issue here is not that concrete is lots and lots worse than a lot of the other materials that are out there. I mean, concrete compared to other materials is relatively low in terms of carbon emission per unit. However, concrete is used in an order of magnitude more than many of the other construction materials that are out there. So we're using so much of it, and everybody wants roads, everybody wants water treatment, everybody wants sewage treatment. Those are some of the things people ask for. So this is where the CO2 is coming from. Now, about 50% comes from the calcination process when the cement is going through the kiln. 40% of that CO2 is coming from combustion, and about 10% is coming from transportation. So really what we're looking at ways to reduce the amount of clinker that we're going to use in some of the binder systems that are out there. So there's really 3 areas that we'll focus in on, and we'll touch in on a couple of these. Reducing cement content comes a lot through mixture proportioning, and that's probably the first step that a lot of people can do to reduce the amount of clinker in their concrete. Improving the life cycle performance. If we're producing concrete that lasts 10 years and we can go out and produce something that lasts 60 years, it's much more sustainable to have the concrete that's lasting 60 years. So long-term, durable concrete is really what we're shooting for. But what we're going to spend most of our time talking about today is the ability to reduce the clinker portion of the concrete. And that's what we're going to spend a lot of time on. Now, the ordinary Portland cement process, cement manufacturing process has shown up here, and many of us have seen this in different classes or different textbooks. PCA has this online. But the whole idea is we're going to put raw materials in, we're going to heat those materials up, we're going to get CO2 being liberated during this system, during the calcination process. We've got the fuel going in, we're grinding the materials, and we're producing ordinary Portland cement. Portland limestone cements are very similar, and there's been reported to be over 1,000 papers on cement systems that contain limestone. The big conclusion out of a lot of these papers is when you add in limestone, you get a dilution effect, you get less of the cement in the system, therefore you should expect the benefits or the properties of those materials to go down. I would point out that in North America, there's been a real push with the Portland limestone cements to really try to provide similar performance to the ordinary Portland cement. By providing similar performance, you could easily substitute out your OPC for Portland limestone cement and continue on with business as usual with the concretes that you're producing. And we'll talk a little bit about that. But the whole idea here is instead of taking your limestone or your calcium carbonate and running it through the kiln, you can introduce it later on in the process. If you can intergrind it later on in the process, now you don't have to heat it up. Now you don't have to have that CO2 that's been given off through the calcination process. You can intergrind it and you can produce a Portland limestone cement. Generally, it's interground to be a little bit finer, but as I mentioned in North America, the whole idea with this finer grinding is so that it's completely interchangeable. So you can swap out the OPC that you're using, swap in the new PLC that's using, and go on down the road fairly quickly. Here's just a comparison of the two, and as I mentioned before, it's a slightly finer blend. And what you'll notice here is this is the OPC up here on the top. Down here on the bottom, we see the Portland limestone cement, and you can see the limestone being the yellow particles. The big part of this is the limestone is relatively fine, right? And that's really where the benefit is coming out in these materials. Okay, so what I want to do very quickly here is I want to touch base on a study that we've recently been doing for the DOT on commercial Portland limestone cements from a variety of different clinker sources. And what I really want to sort of just try to impress upon us is this is a technology that's really ready and is something that can be utilized and implemented relatively quickly. What I want to point out here is we're going to be looking at 4 different clinkers, and I'll show you a few slides of this, so this is why I'm going to take a little bit of time to go through these. 0.38, 0.42, 0.46 water to cement ratios as we go from top to bottom. Clinker number 1, clinker number 2, clinker number 3, clinker 4 is over in here, and what we've got here is a fly ash being added to clinker 2. And what these plots are is they're a plot of the properties of the Portland limestone cement divided by the same cement made with a conventional clinker. So if you get a value of 100%, that means that the Portland limestone cement is completely interchangeable with what you've seen with the ordinary Portland cement. And to make that a little bit more clear, what I've essentially done here is drawn through on a red line the 100% value, and as we go down this particular series of symbols, we go from age of 1 day up to 1 year properties. And one of the things that we can notice very quickly when we're looking at compressive strength with these commercial Portland limestone cements, right, commercial clinker, commercial, all of these give you really similar performance to what you see with the conventional OPC. We're within 95% of the strength, typically across the board. Sometimes we see a slightly earlier strength, higher strength at early ages. Reason for this is because of the finer grinding. Right? By the time we get out to later ages, we're seeing usually the fact that we hit about equivalent performance at 28 days and maybe something a little slightly lower at long-term values. When we've got fly ash in the system, we typically see a slight increase or a slightly kick up in the system. And then the last 2 columns we look at over here are, instead of doing an equivalent system, this is when we're adding limestone to the system, just adding it, not intergrinding it. And typically we can see that effect that we talked about before, that dilution where when we replace 10% of the cement with limestone, we'll notice that the properties drop so that we get 85 or 90% of the overall strength. Similar benefits can be seen, or similar types of trends can be seen when we look at the elastic modulus. Again, 100% value means the PLC system, the Portland limestone cement system, is equivalent to the OPC system. Again, across the board, we see very similar observations. Flexural strength, again, with the commercial systems, the conventional PLCs here shown in blue, PLC with fly ash shown here in green. We see very similar performances. We can start to get down a little bit lower on one particular clinker. But in general, the performance is very similar. Again, the orange and the red show the effect of dilution when you're just adding the limestone into the system and not taking advantage of those finer particles. Similar set times, and this will go against a little bit of what I'm going to point out a little bit later, but I wanted to put this in just as a placeholder, that when you're using the PLC system, you have a very similar set time to what you see with the OPC system. And again, I'm putting this in because it's going to contrast a little bit of what I'm going to show a little bit later on. Transport properties, if we're just counting on dilution, we see a little bit of an increase, but again, For most of the systems, we see a behavior in electrical properties that's relatively equivalent. We see a slight decrease down here, and we think that this is due to a poor solution change with the electrical properties, and that's something that we're still looking at because the chloride ingress numbers are very, very similar. So really the takeaway from the PLC systems, the inner-ground systems, we see a finer grind results in similar strength. They're always within 95% of the parent material. Very similar modulus, very similar flexural strength. We see similar or slightly earlier set times as compared to the OPC when we're looking at the PLC systems. And then we see the electrical properties, and as I mentioned, on some systems, depending upon the chemistry, we can see a slight decrease in the electrical properties, but we see very similar chloride ingress in those particular materials. Now what I want to do is I want to jump into some different ways that we've been looking at fly ash and limestone systems, and one of these is an alternative approach to grinding. So there was a discussion a little bit earlier about can we start reclaiming certain materials, can we start doing other things to use some of these different fly ashes, and one of the things that we've been actually looking at is the approach to use this device over here, and this device is called the jet mill, and the basic idea here is we drop the material in and we essentially get the material moving in an airstream and we collide it with itself. When it collides with itself, it breaks up into smaller particles. And this is a technology that we've been looking at to see if we can reactivate some materials that are out there or make very, very fine particles that could be very, very useful. So we've been doing this at pilot scale evaluations. You can do this on a tabletop unit, but we've been doing this 200-300 pounds at a time in a commercial process, but there are groups that do this for ceramic materials that do tons of materials every single hour. So this is something that can be scaled up relatively easily. After about 2 to 3 passes, we can get down to a material where we essentially get down in the 1 to 2 micron range of the size of the particles, and then continued collisions really doesn't get the material any smaller than that. And this is probably a very active material, which we'll see from some of the data that'll be shown a little bit later. So with the original material we started out, after 1 pass, 2 passes, 3 passes, we can greatly reduce the size of the particles, and this can have great impact on the reactivity of those materials. So to showcase that a little bit, what I've shown here is the cumulative heat that's released in those materials. This is a measurement of isothermal calorimetry, so it's essentially a rate of reaction. Here we can see black. In the black line is the conventional cement system, cement plus 15% limestone, here shown in blue. If we do separate grinding of those materials, we essentially can increase or accelerate the reaction and get more reaction happening. But if we intergrind the materials, again, even faster and higher heats of hydration going on in those materials. So by intergrinding, just like we see in a ball mill or just like we see in other technologies, the limestone gets preferentially smaller than the clinker, and we can see some real benefits there. And again, the benefits really coming at early ages, and that's very important for a lot of these higher volume fly ash systems that you can get those benefits at the early ages. Again, to extend this to fly ash systems, the cement, here we've got the ash and the interground system here being shown in brown. So if we just had the cement, we had the ash system. If we intergrind, we can increase that heat. And again, the strength, we can start to get similar properties at earlier ages through that intergrinding type of approach. So the jet mill appears to have some potential promise, although we really need to look a little bit more at the energy and costs and what it takes to really scale that up. But the real benefit of this is by intergrinding, we can accelerate both limestone and the fly ash, and there's a potential here to start reclaiming some of that ash that's been ponded, because all of a sudden we can get it to be reactivated because we're crushing it and we're getting that material to start to come out. The other thing that we've looked at a little bit, and this has been some work that we've done with NIST, is really looking at set acceleration with limestone and fly ashes. And one of the things that we looked at when we started looking at high volume fly ashes was the potential concerns that start to come up with, well, we'd really like to use higher amounts of fly ash, but we don't know when it's going to set. It's going to have slow strength development at early ages. So that's really some of this work that's gone into this. Looking at a couple different systems, what we've done is we've done a volumetric replacement. So we've essentially have the baseline system is 100% cement, and then we've looked at replacing 40% of the cement by volume with fly ash and limestone, fly ash and 10% limestone, and essentially what we've been doing is looking at different size limestones from about 17 microns all the way down to what we'll call a nano particle, which is in that 15 to 120 nanometer range, to really see some of the benefits of this. And there's a lot of data here. This is Vicat, so this is setting data. But what I want to point out is this is kind of the conventional or the baseline system shown here in this dark blue line, 100% cement. And if we just start to add fly ash to the system, here we look at our 60% cement, our 40% ash system, we would be way over here. So we go from about a 3.5 hour set time to about a 7 hour set time. If we start adding limestone into that system, what we can start to see is this moves back over to this position. And if we take some of this data and we start to plot it a little bit differently, we can see similar trends with calorimetry. But if we start to plot this a little bit differently, what we can start to say is based on the surface area of the limestone that's being added, based on the size of the limestone that's being added, we can actually control when that set time would be. So if we can use finer limestone powders, we can get back to a set time that's really more compatible with conventional type processing. So what you can see here, all right, is that if we're using a 5% limestone or 10% limestone and that limestone is very fine, it's very possible to get back to something that would be equivalent to that 100% OPC system in terms of setting. So we can now overcome some of those delays in set just by combining limestone and fly ash in that system because of some of this beneficial effect of some of the limestone reaction that's going on, but also the fine particles that are leading to some nucleation. And a procedure's been developed where essentially you can run through a series of calculations and figure out how much limestone you would need to get back to an equivalent set or whatever set time you would need. And if you're interested in this, we can provide you the paper that provides a lot more details on this. So fine limestone is really an effective approach to mitigate some of these excessive delays that are going on when you're using higher volume ashes. The performance is completely related to the particle size or the surface area. And then you can essentially develop a linear relationship between the particle surface area, the particle size, and the set time. And there's a couple different approaches that have looked at this. The final thing that we want to talk about here is really an approach that we're looking at to try to extend the use of high volume fly ash with combining it with internal curing. So this is a particular deck. Now this is not a high volume fly ash deck, but this is a particular deck with internal curing. And if you haven't seen internal curing before, and this may sound like a different type of topic, conventionally we have concrete up here, and I would hope, as I mentioned earlier on, that we would be minimizing the paste content. So I hope you have a little bit more aggregate than what I've shown here is these dark aggregates in the system. But the basic idea is we do external curing in a lot of our applications. We put water on the top of the surface, or we put a film on top of the surface, but in a really dense concrete, this water can only penetrate so far into the material. The approach that we're trying to use is instead of essentially just providing water from the surface, we can hide water inside of porous inclusions. We can hide water inside of the aggregates, and when that water is needed, it can be drawn out of lightweight aggregates, hydrate the system, and can provide some of the beneficial components that we would want to see here. So the idea is when water is needed, it's pulled out of the lightweight aggregates, it's available throughout the cross-section to hydrate the overall cement. And there's a quick calculation that you can do to calculate how much water you need. It turns out that you need about 7 pounds of water for every 100 pounds of cementitious materials you've got in the overall system. Okay. Now, what are some of the benefits of this? Well, one of the real benefits of this is you are providing longer times for curing, and especially when you start to look at fly ash, you're providing that water, it's sticking around longer inside of the system. All right. When we conventionally do ponding of the water on top of the slabs, there's a big pressure to keep people there and keep watering the slabs, keep watering the slabs. And we know when we've got things like fly ash, we have to stay there for a lot longer period of time. This plot over here shows the conductivity of the concrete from a plain system to 100% internally cured, which is essentially that 7 pounds per 100 pounds of cement, 7 pounds of water per 100 pounds of cement. And you can look at this and you can say, well, exactly, I knew I wanted a concrete that had 8 times 10 to the minus third Siemens per meter. That's exactly what I needed in terms of electrical conductivity. Does anybody get excited about 8 times 10 to the minus third Siemens per meter? No, because we have no idea really what that means. All right, but the whole idea here is by internal curing, we have water sticking around for a longer period of time. It's hydrating more of the cement, it's hydrating more of the fly ash, it's densifying the system, so it goes from 8 down to a value that's more like 4. You may say, well, I still don't care if it's 8 or 4 or anything else. This number here is directly related to the speed at which ions move through your concrete. And if you drop that number in half, the ions are moving half as fast. It's going to take them twice as long to get to the reinforcing bar. So you're hydrating more of the system. Very important when you've got fly ash in the system, and this comes from densifying the overall material. The other thing that we've been doing when we've been looking at the high volume fly ash systems is, and you'll see this here, we've got a 0.42 water to cement ratio concrete. This is a fairly typical bridge deck mixture. And in order to make the materials have similar strength development at very early ages, this green line shows what happens if we replace 40% of the cement with fly ash. This dark black line here shows what happens if we replace 60% of the cement with fly ash. The difference here is what we've done to offset some slower early strength development is we've reduced the water to cement ratio. So we can reduce the water to cement ratio. We can get very similar performance at 1 day with 40% of the cement being replaced with fly ash. Very similar performance around 7 days if we're replacing 60% of the cement inside the overall system. Now, normally this becomes problematic if you drop the water to cement ratio that low because you lead to cracking problems and other things like this. But this is really one of the benefits of the internal curing. So over here we've got our 0.42 water to cement ratio concrete. If we just dropped the water to cement ratio and did nothing else, we would get this red line with the stresses really building up inside the concrete that could lead to cracking. Right? If we just have the high volume fly ash in the system, we again would see high stresses, and one of the differences is because we're reacting more of the cement, we would see these higher stresses going for a longer and longer period of time. However, if you use the high volume fly ash with the internal curing, you can substantially reduce that shrinkage that's taking place and drop back down to a very similar level of stress development inside the deck. So now you've got a 0.3 water to cement ratio system. You've substantially reduced the transport properties, and you've substantially reduced the shrinkage and cracking potential inside of those mixtures. Okay. And the reason for this is shown as on this plot up here. This is just the heat that's given off, which is a measure of how much material is reacted versus water to cement ratio. Sealed system, internally cured system at 3 days. You're getting about 5 to 10% more of the material reacting because you're supplying water to the system. This gap gets bigger and bigger and bigger over time, and gets bigger and bigger over time when you've got more things like supplementary materials in the system. So keeping water in the system, keeping the system hydrated, right, does exactly what we're taught in Concrete 101, keep curing the concrete, but we're curing it from the inside out. The other benefit to this is because we've reduced the water to cement ratio, because we've provided that additional curing, we can see substantial changes in the electrical properties, which mean we've made the system much more dense and much harder to start corroding the overall concrete. So internal curing has a lot of advantages. We can reduce the cracking potential, we can improve the hydration, we can reduce the transport, and one of the other things that I'll mention here very quickly, and I haven't had time to go through it in great detail, but it improves construction robustness because now we're less susceptible to things like thermal shock in the system. One of the other takeaways, and I'll throw this out as sort of a little, maybe a little taster here. It was discussed before. You can have a lot of problems with air entrainers. We've made these high volume fly ash mixtures at a 0.3 water to cement ratio. We put them through freeze thaw testing. Because the water to cement ratio is so low, we don't see freeze thaw damage in those systems. We can't get water into the systems. We can't get them saturated because they're very dense. So in summary, some of the motivation, really the idea is to reduce the clinker. It helps to reduce the CO2 production. We've shown commercial PLCs from a variety of clinkers, similar set, similar strength, and really the whole idea here is they're at a point where they're really able to be a direct substitution for an ordinary Portland cement. An alternative approach for grinding, jet mill grinding is a technology that we're really looking at. By grinding it increases the reactivity so we can really accelerate the hydration of these materials and maybe reclaim materials that are already sitting on the ground. Set acceleration with limestone, so we can offset some of the slow strength development and high volume fly ash mixes with fine limestones. And then we can use internal curing as a way to help offset some of the slow strength development by changing our water to cement ratio, but then we can account for the reduced autogenous shrinkage, we can improve the curing, and we can reduce things like fluoride ingress in those systems. And with that, I'll turn it back over for any questions if we have time.
Yep, we have time. Any questions? I'm sure there's going to be some questions.
Jason, what impact, if any, internal curing would have on bleeding? And the fact that you still need to apply curing on the surface.
Right, so to answer the first one, we have not advocated installing bad concrete practices. All right, we've done a lot of testing, so we still say do the same curing that you would normally be doing with a membrane, with whatever else you're doing in the system. I will say anecdotally, we've tested the lab where if you have rapid drying, you see a reduction in plastic shrinkage cracking with internal curing. As far as the other question on how does this affect bleeding, there's not a substantial impact on bleeding that we've seen. One of the things we have noticed, though, is these materials are less sensitive to plastic shrinkage cracking because you have that additional water inside of the system.
Internal curing, how are we going to achieve that in our regular mixtures? Are we going to do that with lightweight fine agate, or can we also do this internal curing through coarse aggregate, lightweight coarse aggregate?
Well, conceptually, you can use fine aggregate or you can use coarse aggregate. I would advocate using the fine aggregate because it's better distributed throughout the mixture. And also, one of the things that we've noticed is in certain mixtures, to get that distribution, you have to use more coarse aggregate, and that has the potential to lead to freezing and thawing issues. So we've noticed with the fine materials, we haven't had any problems with freezing and thawing. We have really good distribution, and we use less materials, and they're typically a lower value material because a lot of people want to use the coarse aggregate for its lightweight capabilities as opposed to the internal curing. But both are technically acceptable processes, but you need to look at the whole mix.
Thank you so much.
Okay.
You think about a new type of grinding, is it less energy in this method than the traditional one, or more?
The thing is, right now we're sort of looking up at the scale up. I mean, the tabletop units are more energy per gram of cement than anything else. As we go to the bigger units, that comes down. The real question is, from our perspective, is it an alternative that has us the ability to control the size maybe a little bit better? And I think if we can see some benefits there, or can we reclaim the materials a little bit better, that could give us some potential opportunities. This is real early work, and to start to do a cost analysis that says, we're ready to put a plant in today, we're not at that point. All right, but it's an option that's out there.
Related to the internal curing, I guess I haven't heard a percentage of this porous aggregate that you need to hide the water in.
Yeah, it depends a lot on the aggregate itself. We've done this with aggregates from all across North America. Normally we're replacing about 30% of your sand with lightweight sand.
You've talked about nanotechnology and limestone. Do you have any information or research on how that affects the air void system in carbon concrete or plastic concrete for that matter?
On a lot of these, we've measured the air void system when we go to the full-scale concretes, but we haven't looked specifically at how the nanomaterials alter that. We've measured that we get similar air void systems on the commercial materials, but we haven't really looked a lot at the nano materials and how they're altering it. But one of the things that I would actually, and maybe again I'll put out this teaser for it. We spend a lot of time focused on can we air and train the concrete, and I would actually argue that we could spend as much time saying, can we make concrete freeze-thaw resistant using a different mousetrap? And I think that there's a lot of value in there because all of a sudden we get away from some of these problems, especially when we get to fly ash systems. Can we use a sealer? Can we use an internal waterproofer? If you can keep the water out of the system, you can make it freeze-thaw resistant.
How can we grind nano limestone?
The nano limestones aren't being ground. What I was mentioning with the jet mill grinding is we're looking at more conventional limestones, fly ashes, and cements. And really, with the jet milling technology, you really don't grind things smaller than 1 to 2 microns because of the technology. You can't grind materials finer than that.
For the set acceleration, we use some of
it not?
That's a precipitated one that comes out of Canada, and Taisato would be much better to answer those questions than I would, and I'd be happy to give you his email to answer the nano limestone material.
And so that kind of leads into my next question, is the set itself are you both blending limestone with cement with concrete and flat?
In the studies that we're doing, we're putting the in that particular study, we're actually putting the limestone in afterwards to really control the size. Yeah.
All right, thank you.
Okay, thank you.